next exam is, I don't know, about 4 weeks off, 3.5 weeks off, and covers modules 4, 5, and 6, which if you scan quickly in the text, that is on exponential functions, polynomials, and rational functions. So the functions that we were dealing with the first month of class were all linear functions and other sorts of just basic relationships that we were, doing a variety of types of computations. But what we're going to be talking about next are other sorts of things. So the key relationship with constant rate of change was that for any change in the input, whatever it was, x, the input quantity, the associated change with the output quantity, if you put those two in a ratio together, that change in y over change in x always came out to be the same. As long as you pick the same two, like the x's and y's that corresponded to one another, no matter how large that interval was for x that you chose, the corresponding y, when you do the proportion there, that ratio of changes came out to be the same all the time, or the changes were proportional for any size interval. So that's not true with all sorts of functions. That's true specifically with what are called linear functions or constant rate of change relationships. And those, a lot of times you can think of those as kind of additive relationships in that, let's see, what was some of the examples that we used when we were putting those together? I don't know, you start with 2,000 insects and it decreases by 75 per day, something like that. So you're like subtracting. For every 1 unit change, you have the same amount of, in the input, you have the same amount of change in the output, whatever that amount of change is. And you can obviously multiply and not be talking about 1 unit input changes. Whether it's increase or decrease in the output depends on the problem. But it's when you're moving from one value of the input to the next, if you're thinking 1 unit at a time or chunks at a time of some certain size, you can think of adding or subtracting, depending on the problem, the same amount to the output coordinate. And that's why you end up with this graphically straight line situation. Every time you visualizing, add, go to the right a little bit, and the input, you add or subtract, go up or down by the same amount in the vertical direction, the output coordinate. So we end up with this go over 1, up 7, over 1, up 7, over 1, up 7 sort of effect, or whatever it is. That's just as an example there. That would be a constant rate of change of 7 to 1. Now, exponential and logarithmic functions, we're going to start with the exponentials. Exponential and logarithmics are inverses of one another. We talked about inverses a little bit already, but these are specific types of relationships. We dealt with general functions and weird-looking things with square roots and who knows what else. But in terms of writing functions, the only sorts of functions we wrote from scratch from descriptions tended to be linear things. Whether it was, the box problem, we did the length and width and height all separately. Each of those was linear. Exponential and logarithmic functions are a different sort of relationship. It's a relationship based on multiplication and repeated multiplication. They are inverses of one another. So the exponential one is where you see something that looks like multiplication happening over and over and over again. The logarithms, we'll get to those later, but that's kind of looking at the result of multiplication and figuring out what had to have been done to get there. So in any case, let me just scroll up a little bit here. We're not going to spend a whole lot on the meaning of exponents. Meaning of exponents, those are used to indicate repeated multiplication. They can also be used if they're not whole numbers to indicate the equivalent of square roots, cube roots, those sorts of things. If you have fractional numbers, if you have negative exponents, those can indicate reciprocals. But the reason that those other weirder sorts of exponents have those effects is due to just patterns. If you multiply versus divide, we can think of positive exponents versus negative exponents, just going backward from one to the other. But in any case, exponents typically can be explained in terms of just repeated multiplication. And as I said, exponential functions are about functions where we're repeatedly multiplying. What we're going to do today is go through, look at a few examples that use this, and then talk about how we can construct exponential functions to model a situation that's described by talking about percents and multiplicative change. So percents are a very common sort of amount of change where you have to multiply, because percents are based on relative to something. 50% of something means, oh, half of it. So you do, divide by 2 or times 0.5. 25% of something, oh, well, that's 1/4 of something. Divide by 4, multiply by 0.25. Multiplication and division are essentially, you can write one as the other. But percent changes, if you have to calculate how much something changes, it involves finding a percent of a number, which involves multiplication. And if you're going to do that over and over again, well, it's repeated multiplication. So you can see the topics that we're going to, this is just the chapter in the book. Again, remember that you've got in this rational reasoning site, there's all those investigations, and we're going to look at pieces of a couple different ones today. There's all those investigations, but this is just the text part. This is module 4. I just clicked on the text because I had this list of topics here. So the meaning of exponents, linear versus exponential behavior, which we were just dealing with linear, so we'll do a little bit of comparison. And today we're also going to talk about 3 and 4 in this list, 1 unit growth and decay factors and partial and n unit growth and decay factors. We'll do more with that last one, that part 4, as well as 5, on Thursday. But it sounds very strange just looking at these topics, like a partial n unit growth factor. That sounds like a bizarre, like scientific result. It's not. We'll see what it means in application. It makes a lot more sense than just seeing a way to describe something like this generally. But the idea is the same as what we talked about with linear functions. If I say something like 70 miles per hour, you don't have to go drive for a whole hour before you can calculate how far you went at 70 miles. You can do part of that 70 miles per hour, or you can do multiple hours, any number of repetitions of this 70 miles per hour, including only part of it, like 1/10 of an hour. That's kind of the equivalent of what's meant here by partial and n unit growth factors. Well, what if I don't do this like one time, another time, another time? What if I need to do this 7.5 times? Or this, I need to do something like 2/3 of a time? Or this happens every so often if it's relative to time? Like every 3 months, what happens? Something like that. So in any case, we're going to talk about all of these things eventually, but the first half of them almost about today. So let's see, what I really wanted to get to in here though was the investigations. I want to look at module 4 investigation number 2. Not all of it, just a piece of it. Because, let's see, is this going to expand on its own? Apparently not. This is about comparing linear and exponential behavior. So the top of this is just what I was talking about. Linear functions are a constant rate of change. Now we're going to be talking about something else. So we're going to be using the same setup for several questions here. So I'm going to take a careful look at what this says. If you have your own device and can read it more easily on that, please do. But we're going to be talking about 2 different devices. Think of them as a cell phone or whatever you want it to be, and how their value changes over time. So product 1, the iTech device, current resale value is $300, and the resale value is expected to decrease by 30% per year for the next several years, at which point nobody cares about it anymore. You can throw it in the trash. Product 2, current resale value is $300, and its value is expected to decrease by $45 per year for the next several years. So thinking about that, just question 1, there's going to be a table down below if you don't have your own device to see this. But question 1 asks you to find the expected resale value for both devices 1 year from now, and think about how you determine those, what operations you used. But take a minute here for each of those 2 to figure out what its new value would be in dollars 1 year from now. And then part B to this question, just to think about it sort of thing. 6 years from now, I'm not necessarily calculating out all the values, but 6 years from now, think about, well, which one would be worth more? Alright, so the first product, the iTech device, the one that's decreasing in value by 30% per year, just after 1 year, 30%, it's almost a third. What would its new value be? You don't have a new value for the iTech device that decreased by 30% after 1 year, what its new value would be? Well, what is 30% of that? That's the amount it has to decrease by. 90, yeah, so it'd have to decrease by 90. How did you find that?
300 times 0.3.
Yeah, 300 times 0.3. 30% means 30 out of 100. And you can think of it like a fraction. But if you were, 30 out of 100 or 30 hundredths, that's 0.30, 0.3. So I need 30% of that number, 0.3 times that number, and that makes $90. That's how much it decreases. So what is the new value then? If it decreased by 30%, its value is more than $90. What is its value? Yeah, 210, right? Because that's the amount it decreased. So if the value started at 300 and it decreases by 30%, its new value is $90 less. The new value isn't $90. So there's another way you could get to that result besides that was like maybe 2 steps, like find that $90 and subtract. How could you find the $210 all in one operation? Anyone have a quick way to get the value after the discount? After the reduction? The value's 30% less than it used to be. What percent? Yeah. Yeah, multiply by 0.7. Yeah, if you've got a value that's 30% less than it used to be, another way to say that is that the new value is 70% of what the old value was. So if you decrease by 30%, then you keep 70% of the value. So you could read this problem as you're losing 30% of the value from year to year to year. Or you could also say I'm keeping only 70% of the value from year to year to year. It's complementary percentages, and more often you maybe think about this with like discounts. If it's 25% off, then you have to pay 75%. This isn't a discount, it's an unfortunate effect of technology over time, but it's the same sort of idea. If the value is 30% less than it used to be, then that means it's 70% of what it used to be. 30 and 70 make that 100% total. If it maintained 100% of its value, that means it would be the same value all the time forever. Which that's not going to happen, but some things don't decrease over time. Some things just have a constant value, and that's how they are. This is described as decreasing by 30% per year. And again, just decrease by 30% per year means the same as maintain only 70% or reduce to only 70% of what it used to be from 1 year to the next. So in that case, to find that value after a year, it involves multiplication, whether you do it in 1 step or 2 steps. But it involves multiplication to figure out that new value when we have a percentage like that. What about for product to the Dynasystems device, current resale is $300, the resale value is decreasing by $45 per year. What do I do to find the new value? Just subtract, right? Yeah, decrease by $45, not 45%, just $45, I had dollars, now it's $45 less, I subtract. So $255, right? So after 1 year, product number 1 went from $300 down to $210, and product 2 went from $300 down to $245. They decreased by different amounts. They're described entirely differently. One's in terms of a percent and one's in terms of dollars difference. What about, and this isn't a question quite on there, the next question is like after 6 years, what do you think is going to have the higher resale value? In the next year, year 2, by the end of the 2nd year, if I want to find the value of these two, this is kind of related to this table of values. There's a lot of extra stuff in this. We'll talk about the outside parts of this. But this first one, take a look at this table. We just filled in, this is iTech device. This is the one that was the percentage change. Went from 300 to 210. And the one over here went from 300 to 255. If I want to find the next year value, I'm just writing up the decreases since I've scrolled past them. But number 1, the one on the left, that iTech device decreases by 30% per year. And number 2, the Dynasystems device, as a $45 decrease per year. So to get from here to there, we did that find 30% and subtract, or if you want to do it in one step, find 70%, and it came out to 210, which is $90 less. Let me ask this question. To get from here to there, from 210 to this next number, whatever it's going to be, is it going to be subtract 90? No, it's not. Because 30% isn't always $90, right? 30% of 300 is $90. But if the value of this decreases by 30% per year, that's relative to something. So relative to its value of 300, 30% was $90 decrease. But if the value is only $210, if it decreases by 30% from this, 30% of its value goes away, it's 30% of a smaller number that I'm losing. So more tedious number to work on, because 300 kind of rounder number than 210, but I need to decrease this value by 30%, or find what's the complementary percentage. What's left over then is 70% of this, and you can do it either way when you're doing these computations. Find 30% and then subtract it off, which also then tells you the size of the change. 30% times 0.3 sounds like 63. Just multiplying by 3 kind of quick in my head. So 30% is $63. And I don't know what that, let's see. If I subtract 60, that sounds like 147. But sometimes looking at the numbers, like, which of those changes is larger? Oh, this went down by $90. That went down by $63. So they're weird numbers in terms of the dollar amount of the change. And looking at this table, I've got exactly this here. So I've got 300, 210, and 147. This first change was negative $90. the next change is negative 63. It's still 30%, but it's 30% of a different number, or 0.3 times a different number. 30 times 0.3 was 90, subtract it off. 210 times 0.3 was 63, subtract it off. We're losing 30%. You could also say, like I said, we're keeping 70%, but I did want to talk about how large these changes are. See what you can do with the rest of these tables, including the one on the right, which is probably much easier. The one on the left likely involves a calculator from here out. Not such nice numbers. Exponential functions, when you're not dealing with the simplest numbers, tend to be a little bit tedious and calculatory. We're going to look at that next. This is just in your textbook. So some optional reasoning sake. But yeah, we'll look at that one next. Yeah. Which isn't in your textbook. Was it? Yes. Yeah, this is module 4, investigation 2.
I'm not seeing investigations.
Wait, did you tell me about that problem with the previous module?
I haven't addressed it. It's one that I will do it.
I will talk to the tech person again and say it's also happening with mod 4. Alright, so not particularly easy numbers to deal with in this case, but if you can see what the patterns are, once you figure out, maybe just by looking at the description and figuring out a couple of values, that, oh, if I need additional values, here's what I can do, here's the computation I can do repeatedly. If it's a specific type of change, there's usually a specific way to compute the new values. So in this case, I said you can get the values in one step or two. When we're dealing with this 30%, use the 30% or use its complementary percentage, the 70%. Losing 30% is keeping 70%. And if you just want to go through these numbers without calculating the amount of change first, just do times 0.7, times 0.7, times 0.7. Keep 70% of that and 70% of that, which makes a smaller and smaller and smaller number. Let's see. Here, I can do it on here. So if I multiply by 0.7, I get the 210. And do it again, I get 147. And after that, not particularly nice numbers, but this would be after 3 years have gone by. So I've got 210, and then 147, and then 102.90. This is dollars, so it's okay to have decimal values. It's not a number of people or something. And then times 0.7 again. This would be after 4 years, just a little over $72. After 5 years, about $50. So you can see it was like 72 and then 50. It's only decreased by 20-ish dollars, but that it's still decreasing by 30%. It's just decreasing by 30% of an increasingly small number. So that amount of decrease, the dollars decreases. The amount that we're subtracting each time is smaller and smaller, but the percentage that that value has relative to what we were starting from is the same. So if I'm looking at these numbers, this delta x, or delta s rather, I suppose I should say here, since that's the value. The change in time is always 1 year. The amount of change in the value of this device number one, the iTech device, that change is getting smaller and smaller as an amount of dollars. So it was $90, then $63, then I don't even know, smaller and smaller amounts of dollars as we go down this table. Now the other one, the Dynasystems device, that's the one where it's decreasing by $45 per year. So in that case, this one's easy. Negative 45, down 45, down 45, down 45, down 45, until the end there. Decreasing by the same number of dollars each year, which I don't know if that's easier or harder to subtract, but we started out with 300, subtract $45, and that was $255, and then do it again. We're never going to end up with change. It's going to be whole numbers of dollars since we're just subtracting whole numbers of dollars, so mental math may be a little bit easier, except 45. So what was that left? 210? After 3 years, it's down to 210, whereas, well, after 1 year, 2 years, third number here, this one was 210 after a single year. But this one keeps dropping by 45 all the time. The one on the left is dropping by increasingly small numbers. So this is at the beginning. I guess, let's see, they have these labeled. Years from now, 0. 1 year, 2 years from now. Right now, 1 year from now, 2 years from now. So you can see they started at the same value. This one dropped rather quickly. This one's dropping at a constant rate. If I were looking to graph these, let me pull up Desmos. If you've not used Desmos before, it's a very handy online calculator, and for graphing things, not too hard to use. If I wanted to graph this pattern of numbers, now there are ways to put in tables of values and have it plot them, but this is something that we learned how to write equations for last chapter. Right, it starts at 300 and drops by 45 per year. So if I'm having years as my horizontal axis, I'll just call it y's and x's. So Start at 300, go down 45 per year. Anyone know what equation I could write in terms of just y's and x's? Thoughts? Start at 300 and go down by 45 per year for however many years we want. Now, I'm going to have to rescale this because I know I'm looking at values that are around 300 and I don't care about large or negative values of x. I just clicked on, if you haven't used this site before, I just clicked on this little wrench here and it gives you ways to change the window that you're looking at. I'm just going to look at 0 through 10 on the x-axis. And I know for the y-axis I need to go up past, like, maybe I'll just put it to 300. I don't really need negatives. But let me scoot this so we can see the axes. And you can use your, scroll in out with your fingers too, but just to get this kind of on there quickly. That's what's happening with device number 2. Starts at 300, goes down by $45 per year. 300 is dollars, 45 is dollars, well, it's dollars per year, so 45x would be a certain number of dollars. Go down by $45, going down by a total of 45 times 2, a total of 45 times 3, and so on as time goes on. And any number in between, really. I don't know if we're going to talk about, well, what about after 2.7 years? If it followed the pattern, it'd be between after 2 and 3 years, but who knows who's calculating how. Now, this one, we started at 300. If I want to think about how do I get to 210, and then to 147, and then to whatever weird number is next that we had on there, 120 something and change. Well, I can keep the whole thing and then subtract 30%, or I can keep 70% and just state that value. That sounds like an easier thing to type. If I want to know what's, start at 300, oops, and keep 70% of that. After 1 year, oops, where'd my decimal point go? There we go. After 1 year, that's what I do, right? 300 times 0.7. Now that's just a constant value. That would be 210 all the time. That's not what I want. After 2 years, I want to multiply by that 0.7 again, take that result and multiply by 0.7. So I'd be doing something, I'm just kind of writing what I'm thinking here, and we'll put this together. After 2 years, I'd need to do that. And my decimal just keeps not showing up. After 3 years, I'd want to do that. After 4 years, if you can see the pattern here, I'd need to take that result, whatever it is, and multiply by 0.7 again, or find 70% of it to state the new value. So now, what those were, that was just a sequence of what the values are after 1, 2, 3, and 4 years. If I want to state it in general after X years have passed, I don't know how many times to write times 0.7. So I'm going to write time to the x power. I don't know if you can see that. To the x power, because an exponent, whether it's a 1 or a 2 or a 3, tells me how many times I'm multiplying on this factor. Now in reality, it doesn't have to be a whole number, but thinking about if that was a 1, that's 300 times 0.7. That's after 1 year. If it was a 2 in that exponent spot, 300 times 0.7 squared means 300 times 0.7 times another 0.7, which is take your 70% value from, which is the after 1 year, and then find 70% of that. So it's after 2 years. Multiplying by 0.7 repeatedly, we can write as multiplying by 0.7 to a power, but that power was how many years have gone by. And so here's this curve thing is what we get if I graph all the values for not just whole number powers of x, but all real number powers of x that we've got going on here. So some of those are bizarre sorts of powers. But I can think, well, after 2 years, this value is 147. After 2 years, I've got 147. This is 140, and that's 160. So this is fitting, and you can also click on these graphs After 2 years, let's see, 147. Tells you the points. You just have to, if you're close to where you want but not exactly, just wiggle your finger a little bit. There, after 4 years, $72.03. Now they're going to be rounded off decimals in a lot of cases that are like longer decimals, but it just shows you some of them. But in lieu of like, if you're just at home working on stuff, instead of trying to, where do I put my graphing calculator, or it needs charging, or whatever, it needs batteries. If you've got your laptop charged up, you can use this website, it's free. You can graph things quickly, analyze them a little bit, take a look at the patterns. And you don't have to know any fancy computer programming stuff. You just type it in just like you would on anything else, or how you'd write it, essentially. But in any case, you can see this, the formulation of these. This is a linear function, like y equals mx plus b. And I don't have to write 300 minus 45x. I could write negative 45x plus 300, if you like to see it in that order instead. That's obviously the same. You can add in whatever order you want. This one, I could say, 0.7 to whatever power, and then times 300 afterward. But the reason I have them written this way is just kind of the way we worded the problem. These phones started with or whatever they are, devices, started with a value of $300 and then changed from there. So I just started by writing the 300 and then how we compute the change after that. Where x in these cases is taking the place of the t that was in the problems. This likes y's and x's. I think you can change them to something else, but in terms of this, I can subtract 45 repeatedly, which would be subtract 45 times, however many times I want to subtract it. I can find 70% repeatedly, 70% of a different number every time. Just kind of like subtracting 45 every time isn't always subtracting 45 from 300. It's subtracting 45 from whatever you just got the last time. This times 0.7 to the x doesn't mean I'm always finding 70% of 300. I'm finding 70% of whatever I just had the last time around. If you want to think of using whole numbers of x, every time I increase x by 1, in the top case, my number is $45 smaller. If I increase x by 1 here, my answer is, 30% smaller than it used to be, or it's 70% of what it used to be, 7/10 of its previous size, or 3/10 smaller, 30/100ths, however you want to say those. So in any case, though, if we want to do this whole table after 6 years, looking at this graph here, there, after 6 years, you can see they're pretty close to the same value. They started out at 300. This one dropped really rapidly. And you can see that in the graph. That blue line decreased really rapidly, but it's a curve. It's not a straight line. I said line, but just following the path. That blue path drops really rapidly at first, but then levels out because, 30% decrease off of smaller and smaller numbers is smaller and smaller dollar decrease. So by the time I'm around 6 years later, they're actually quite close to the same price. Not because 6 is something magic, but just the way that these worked out, one decreasing at a constant rate and the other decreasing at a percentage rate, made them kind of catch up. They're kind of like the tortoise and the hare. One had a head start and the other eventually was going faster and caught up to it. Not the same sorts of functions, those were both linear, but same effect. Eventually, these end up in kind of the same place. And it's just before 6 years. And by same place, I'm not talking about a physical location. I'm talking about just before 6 years, according to this, the two devices would have the same value, which seems to be not very much, slightly under $40. So right before 6 years, the value is a little bit under $40 for both devices, even though they were decreasing with different patterns. Now, you can see this red line. After, 7.5 years or so, suddenly your red device, the Dynavision or whatever it was called, has negative values. probably doesn't make any sense. They're not going to charge you to charge you more to give it to them. Maybe they will, recycling fees and whatnot. But past a certain point, sometimes relationships like this don't make any sense anymore. Just like anything else, we have to consider the domain. So that's why the 6 years was kind of asked about. Past that, it's probably not really feasible to think about. And this blue one, well, if we go 100 years into the future, it's still going to have a few cents worth in value according to this graph. Probably not. No one really cares about it after that long. But presumably, though, you can see if I keep finding something that's 70% of the previous value, it's never going to turn into 0. Because if I have a number and I find 70% of it, it's never going to turn in, it's never 0. It's going to still be something positive. It's never going to be something negative. So that's why this blue curve, let's see, by 20 years into the future, we've got a 30-cent device. Yeah, I don't really care about the value of it at that point. Probably not something we need to worry about. So what I want to take a look at is some more examples of writing the functions like we did here, focusing on the second variety. I've got a couple examples that I want to show you that are not from your textbook, so I'm going to pull them up. I have them in Canvas, maybe. Let's see, where's Canvas on here? There we go. Is it going to make me log in the hard way? Oh. Safe for today. All right, so I just posted this right before class. So examples used in class Tuesday, February 15th. That's today. We're going to use them now. So I've got another copy of this that I'm going to be able to type onto. So this has a bunch of examples related to writing exponential functions. We just wrote one. I want to think about this first one because we've talked about 1 and it was an exponential decrease. This first one is talking about annual raise. We're going to talk, and when I say exponential, that means the exponent is the part that I don't know what it is. The exponent is the part that we're letting vary. The number of times that we apply this multiplying relationship is the part that's the unknown in terms of our input. So annual raise here, and then there's a couple more examples on here that I'll let you work on your own, kind of. We'll go through together. But this first one, suppose your company hires new employees with starting salaries of $30,000. Assuming they do well, you get a 4% raise annually. So if I want to write a function that models your salary after X years, now I'm going to pull up one that I can type on. So it's an increase, right? A 4% raise is a 4% increase. So thinking kind of along the lines of what we did with the last one. What I'm interested in tracking is what's my new salary. I don't want to know what's just the 4%, although that's a good part of that. But we're starting at $30,000 and we want to increase by 4%. So think for a minute about how would you find your salary after 1 year? And then maybe how would you find the salary for the next year after that? And what we're going to do is write a general formula for how you find that after X years. We could use that to find 5 or however many years. But think about 1 year. And I'm just going to use, like, let's see, what letter should I use for annual salary? I'll use A. And it's talking about X years. But what if I want to know after 1 year? I started at 30,000. And then I get a 4% raise. How can I figure out what, not my whole new salary, but just what's the amount of my raise, my increase, if it's 4%? What do we do? 4% means 4 thinking back decimal wise, that's 0.04. So is this it? 30,000 plus 0.04? Does that give me a 4% increase in my salary? No, that would be a 4-cent increase. You'd be really mad if you got a raise of 4 cents per year. So we don't want to add 4 cents. We want to add 4% of our current salary. Right? So if I want to know 4% of 30,000, oops. I want to do that, right? 30,000 plus an extra 4%. Now, that's kind of an annoying formula, right? 30,000 plus 0.04 times 30,000. That's kind of the equivalent of the, if you're doing this the long way, like find the percent and then subtract it. If I want to find 30% off, then I figure out what 70% is, what amount I have remaining. Well, this isn't an additive one. It's a little bit weirder looking. But if I had 30% and then I add 4% to it, it's not a complementary percent. I don't care about 96% because there's nothing that's going away. But I'm keeping all of the original and tacking on an extra 4%. So my ending salary is more than my original salary. It's more than 100% of, more than all of my original salary. In fact, if you want to look at this algebra expression, or thinking of it as an algebra expression, factoring wise, if I were looking at that, I'd say, oh, well, 30,000 shows up in there twice. What if I factor out 30,000? I'm just putting in the commas to like, otherwise it's dizzying numbers of zeros. If I factor out the 30,000, I could write this as 30,000 times 1 plus 0.04. I'm going to get rid of the rest of this. Would you agree, algebra-wise, following rules, those two statements are equivalent? 30,000 plus 0.4 times 30,000 is the same as 30,000 times 1 plus 0.04. So interpreting-wise, and obviously, if you want to write this a different way, I could write this as 30,000 times 1.04, right? Because 1 plus 0.04 is 1.04. I could say, oh, well, like in the previous example, when we took this value and multiplied by 0.7, we found a value that's 70% of the original. When I'm multiplying by 1.04, I'm going to multiply by something larger than 1 gives me a larger result, right? Multiplying by 1.04. 1.04 is the decimal equivalent of 104%. All of the original with an extra 4% tacked on. So if I'm trying to do this increase by a percentage, I'm going to be multiplying by a number that's larger than 1. It could be larger than 7. It could be any amount larger than 1. This is just a little bit more than 1. It's 4% larger than 1, in fact. But multiplying 30,000 times 1.04 gives me a result that is the equivalent of doing find 4% and add it back onto the original. It does that all in one step. That way we can do kind of similar to what we did with the first cell phone. Instead of like find 30% and subtract, we just find 70%. In this case, instead of find 4% and add it, we're going to find 104%. So this is after 1 year. If I wanted to find after 2 years, I need to take that previous result and make that one larger. So this would be my starting amount rather than 30,000. And then I'd want to make that whole result bigger by 4%. And I could use like, brackets or something, but it's all multiplication. Say like, okay, here's my starting amount, whatever that is. Like, was that 31,000 and something? 4% of 30,000 sounds like 1,200, right? Yeah. So that's my 1,200 down below. But if this is my first year's salary and I want to make it bigger to find my second year's salary, like get myself another 4% raise, I'm going to multiply by 1.04 again. So the inner part is, so I started with 30,000. I got a 4% raise and found my new salary by multiplying by 1.04. I'm getting a 4% raise again. So I'm going to take that answer, that new salary, and increase it by 4%. So find the 4% and tack it on. Multiplying by 1.04 is the same as multiplying by 1 and multiplying by 0.04 and adding them because of the distributive property, how that works. Whether it's algebra or just all numbers. That's what algebra is. It's like, how do numbers work in general? But we don't normally think of it that way. You don't think of using these sorts of rules with all numbers. Think of it like, oh, distributive applies to algebra, not to numbers. That's why it works with numbers. So in any case then, this a of 2, weird number, let's see. Don't know what the value is. 30,000. After 1 year, I multiply by 1.04. I get my 31,200. If I want to find my salary after a second raise has happened, I still need to multiply by 1.04. Get this weird number, 32,448. But what that is, expression-wise, it's the same as this. I've got a 30,000 and a couple of 1.04s added on. 30,000 with 2 raises of 4%. So I could write it as 1.04 squared multiplied on, because it's 1.04 multiplied on and then multiplied on again. The 30,000 is only in this computation as a factor once, but if I want to keep increasing by 4%, that means I want to keep multiplying by 1.04. Repeatedly keep all the original and tack on an extra 4%. Keep all of that original and tack on an extra 4% of that larger number. So we get this, whatever that number was, 32,448. But if I want to talk about in general, after X years, once you figure out what the pattern is, what the computation you'd need to do to find maybe the first year or the second year or the first, whatever the time frame might be or the input might be, the first change and then after the second change, once you figure out what the pattern is, we can maybe more easily write what I need to do to find my salary after not just 1 year or 2 years, but any number of years that I'm going to call X. And so if you can see, well, I'd have to start with 30,000. And then depending on how many years I'm looking into the future, I'm going to multiply by 1.04 some number of times. 1.04 as a factor in this process, X times, X years into the future, means I'm multiplying by 1.04 to the X power. And you don't have to, like, I know sometimes what I think is confusing about looking at something like this is like order of operations. You think, well, I have to do the 1.04 to the X power first, and that isn't really what happened. First, I started with 30,000. But when you're looking at this, just remember that exponents are repeated multiplication. So if I knew what X was, I could write this out kind of in sequence how it goes. 30,000 times 1.04 times 1.04 times 1.04 times 1.04. It's just I don't know what X is, so that's the only way I have to write this succinctly is with an exponent of X. But once you know what a value of the exponent is, if it's a whole number, you could write it out as repeated multiplication and then see something that seems like to be the order of operations that you'd think. But it is all multiplication. There's no addition or subtraction between the 30,000 and the 1.04. The only addition subtraction in here is that you might think of this as 1 plus 0.04. I'm going to put a leading 0 on that just to emphasize this. I know from a distance decimal points disappear. But yeah, 1 plus 0.04, that's the only addition subtraction we're really doing. And that came from all of the original plus an extra 4%, an extra 0.04 tacked on. So if you want to find the salary after 5 years, if you don't have a function written out, you can do this one step at a time, like, oh, and then times 4% and add it back on, and then find 4% and add that back on, and you can keep doing that. But if you can find a general pattern, something like this, write an exponential function, you can say, oh, well, all this is asking for is find a of 5, right? So that means I'm starting with 30,000 and multiplying by 1.04 over and over again. How many times? 5 times. After 5 years, after 1 year, it's times 1.04 once. After 2 years, it's twice. 3 years, I do that again. 4 and 5. So the exponent matches the number of years into the future. So I could just do this computation and have it done with. I can also, just keep doing this manually. Times 1.04. That's after 3 years, and so on and so on. But if you can write the formula, you can get there without knowing all the years in between. You don't have to work from one value, 1 year to the next, to the next, to the next, to the next. If you can write a general expression that helps you do that computation repeatedly, you can just substitute in and get your result. Just make sure you know what the values are. This is after X years, so X years after you started working at this job. All right, so keeping that in mind, the second question that's on here, I must have an extra space there. There we go. Monthly price cut. When a new cell phone's introduced, it's priced at $700. Every month, the price is reduced by 2% relative to its price during the previous month. We want to write out a function that models the selling price M months after its introduction. It just says after M months. So if you can write this, think about whether it's an increase or a decrease. See if you can write the function and then at least an expression. If you have a device on you, you can maybe do the computation. What's the price if you waited until 6 months after release to purchase it? So this one is a price cut situation, so I need something that's decreasing. So I know I'm gonna be multiplying repeatedly, since it's a percentage here, a percentage decrease. I'm gonna multiply repeatedly by something less than 1. Got 4 options up here. I've seen all of them on questions like this before on quizzes and tests. Of those 4, 1, 2, 3, 4, I just called this function P for price, after M, once the M was given. But if I want to write this function here, of those 4, 1 is correct. Any ideas? 1, 2, 3, or 4? Yeah. 3, yeah. Number 3 here. So I've got 700 times 0.98 to the m power. Where does 0.98 come from? I don't see any 98s or 0.98s or anything like that in the question. What on earth is that?
It's a decay value.
Yeah, it's the other part of the percent. So this is the value that we're keeping, 98%, 0.98 of the original amount. 98 out of 100 pieces of it are kept. When we have a 2% decrease, a 2% discount. So it's that complementary percentage. Now, thinking about what we didn't do this the first time we talked about, like the 30%, 70%, we just kind of did it. But in terms of this, it's this one, by the way. If I wanted to think about this similarly to the 1 plus 0.04, P of m, it's all of the original, but minus 2%. So after 1 year, I can say like, oh, 700 minus 2% of 700. 700 times 1 minus 0.02. And then the next year I could do that over and over and over again. Sometimes easier to see that smaller number, like a less than 1, because of those complementary percentages, 2% and 98%. If you had everything and you got rid of 2%, then you have 98% remaining, as opposed to thinking of something like 104%, a little bit weirder. But that 0.98 that's in there comes from the complementary percentage to 2%. 2% is gone, so 98% is left, or 1 minus 0.02 in decimal form. So this, in the previous question, the 1.04, in this question, the 0.98, the number that's the base of the exponent, the thing that we're multiplying by repeatedly to get future values, that number is typically called in general a growth factor, although in this case it's not growing, it's shrinking, but general name for it is typically called a growth factor. It's the thing that you multiply by. It's not specifically the growth percentage or a decrease percentage, it's just the thing that you have to multiply by to do the generally kind of 2-step operation that you want. Find the percent and subtract it, or find the percent and add it on to the original, which is a 1 plus a percentage or 1 minus a percentage in decimal form. So this, just the base of the exponent part, this 1 minus 0.02, otherwise known as 0.98, 0.98, that's called our growth factor. Even though in this case, it's a general name. You can call it a decay factor if it makes you happier. But it's like a change factor. How about that? Kind of like we had a constant rate of change. It could be increase or decrease. Here's our constant factor of change factor. It can increase or decrease depending on whether it's larger than 1 or smaller than 1. Now, if it was exactly 1, if I multiply by 1 repeatedly, nothing's happening. That's a very boring function. We wouldn't probably bother writing it, but it would just be constant value all the time if we did. If we had 700 times 1 to the power of whatever, it's just going to be 700 always. Now, so relative to this question, what would be the price to purchase the phone if you wait till 6 months after its initial release? Well, we have a formula for that. This highlighted one, or this form of it over here. We need 6 for the number of months. So not that number, but I need to do a 0.98. I'm going to do that to the 6th power. Do I have this on here? I don't even have an x to the y. sorry, bizarre, non-useful calculator here. That's the 0.98 to the sixth power. Notice what that is. 0.98 to the sixth power is 0.88 something. You could, if you work that out in advance, it actually tells you something. It means like, oh, after 6 months, I've lost about 12%, 11.5%, or I have 88% of the original value. Now, it's not exactly 88%. So 2% per month is not exactly the same as 12% after 6 months. It's close, but it's not the same because it's not 2% of the same number every time. It's 2% of slightly smaller numbers every time. But since they're only very slightly smaller, that's why this is only slightly different from 12%. And what I mean by 12% is complementary percentage. This is 88.58 something percent. That means I've lost 11.4 something percent of the value of the phone. So that the new value is times 700, $620 and a few cents. So the value after 6 months would be this, but thinking about just that change factor, growth or decay factor on its own, raised to a power, that can tell you what the overall percent change is from the original after multiple instances. So after 6 months in that case. If I wanted to know not what the dollar amount changed, but what the percent change in the value is after 10 years, if I say, or not years, months, 10 months here, I'd have that 0.98 to the 10th power. So 2% per month for 10 months in a row is, not quite a 20% decrease. I've got 81.7% of my value remaining, whatever that is. 81.7% is like a, what is that, 18.3% decrease? Doing mental subtraction, which I hate. So just the growth or decrease factor to the power, to a numerical power, you can see what the percent change is after that number of, whatever it is, months, years, whatever the input variable is that you're using. You can see that on its own. Now, another way to see that is by comparing the beginning and the ending values. So this was after 10 months, all right? So if I had 700. So let me just jot this on the board. I'll just use this space down here. After 10 months, the value is $571.95. $571.95. That's after 10 months. The original price was 700, right? If I want to know what percent decrease that is, I can find it a couple of different ways. The easiest way to figure out what part of this is this. If I want to know what percent this is of that, or what percent the decrease is, I can either figure out how large the decrease in dollars is compared to the original 700, or I could find out how large this is compared to the original 700. And use either of those. So if I do the eventual price, if I want to know what percent that is of 700, that's division, later price divided by original price. That tells me what percent this is out of that. Finding what percent one number is of another is telling you how large those two numbers are relatively speaking. So like 3%, that's 3 out of 100. Like 3 pieces compared to 100 pieces, that's very small. The later price divided by the original price here, if I do that, $571.95 divided by 700, this is that 0.817 number, which indicates this 571 something, 571.95 is 81.7% of the original. What's 1.7% of the original? The new price, this later price is about 81.7% of the original, rounded. Now, if I wanted to know what percent decrease is that, I could go back and do division again. I'm like, oh, well, if the value remaining is 81.7% of the original, then the percent decrease is the complementary percentage here, 18.3%. So, oops, sorry. So there's two ways to kind of say that. But that's just by doing, 100 minus 81.7, which is, what did I say, 18.3%. If you want to find the percent decrease just from, like, on its own, you could also say, oh, what's the amount of the decrease compared to the original? That would tell you what percent decrease your price had. What's the percent decrease? Find the amount of the decrease, dollars divided by the original. Don't have that number worked out here, but what is that? 128.05. Just, that's how much different these two are. 0.05. But if I do this division compared to the original, guess what I'm going to get? 18.3%. Approximately. Yeah, rounding the percentages because those numbers are not nice, even numbers. But to find the percent decrease, I can find the amount of the decrease divided by the original, or I could find what percent isn't there anymore. You can find it as a complementary percentage. But when you're figuring out what percent something is of number A, you're going to do a division where that number A is the bottom. So it's compared to that bottom. So just like 3% is 3 compared to 100. If I want to know what percent is something of number A, I do sum of whatever the random other number is divided by number A. That number A is the basis for the comparison. It's the bottom of the fraction in the division. But how you find the top number, you can find sometimes the complement of what you want. Just make sure your description makes sense. So when I do later divided by original, or like the 10-month price versus the original price, that tells me what percent 10-month price is of compared to the original. But I can use that to find how much it decreased then. All right, so let's see. Anything else I wanted to mention on here? There's another question on here. We'll talk about this one next time. But take a look at it between now and Thursday. This question about compound interest. It's a little bit more messy to put together. The numbers, if you're calculating out values after time, are certainly messy. But you don't have to know like a special formula off the top of your head. It's just exponential change. It's this percentage increase when you're earning interest. So it's just very small percentages of interest in this case. See if you can use the same strategies we used for the previous two questions on this sheet to put together a formula that calculates the value of this account over time and answer the other question. All right, that's it. I will see you next time.